Jason. Here's our presentation for this.
Self-adjusting Newtonian telescope for our final project.
Yep.
This is the initial mount that was Andrew handmade, you know.
Right after the first
presentation, yeah.
It's made of just a bunch of
Aluminum
pieces.
with a 5mm rod just threaded through the center of the entire thing.
Mass, and the entire thing just sits on the two arms.
Some of the issues of it is it wasn't exactly through the center of mass. You know, the holes were predetermined because of the way it was designed, so it wasn't exactly through the center of mass. So one of the issues that we ran into was that it just kept falling forwards.
Instead of being like holding its position like this one, if I do like that, it just holds.
It just holds itself. It's pretty good.
It will tend to just plummet.
Yeah, this one will tend to plummet.
The purpose of this mount was just making it easier to aim, like rather than holding the entire thing and like hoping that I can use a nearby railing or whatever to prop it up for me. I can just like point it at something.
And then it'll work out, yeah. The other issue was that the lazy student sometimes jammed itself because it took it off an old TV mount. Like you can spin this, the new one you can spin very, very freely. The other one is just like sometimes you just like
it just got stuck.
Yeah. Sticks. So this is the final mount that we made. It's just a belt and pulley. You can see it's a 22:48 tooth ratio. And originally we were going to do a gear system to turn the base of the thing, and we changed our mind and just ended up putting the stepper motor straight through the top part of the Lazy Susan and the bottom part of the Lazy Susan, like what the Lazy Susan sits on and what the Lazy Susan is attached to.
It's less parts, and it also makes the power thing just self-independent, I guess.
Like you can spin this like a few thousand degrees.
Yeah.
It won't.
Yeah.
The wires won't tangle. Yeah.
Yeah. Like currently the force has an issue, but like otherwise all the controlling interfaces just sit on the telescope itself.
The issue itself being that it needs to connect to the computer in order for you to change the code.
We can make that wireless eventually.
Yeah.
And of course the final thing, the camera. That thing, we bought a dedicated astronomy camera. This thing has very low noise, so it doesn't capture random white spots and like other noise in dark environments. It also has it's in special software, so it's very easy to adjust like the exposure and gain settings of the camera itself, and highlight efficiency. It basically it captures all the light instead of like some of it.
Yeah.
This astronomy is used through is connected by prime focus, so directly to the mirror, to the primary mirror, without any like lenses or anything intermediate in the middle.
Like you can see, if I take a stop right now, you can just see straight into the
camera.
Straight into the camera. Yeah.
There's no like camera lens. There's also no telescope lens.
Yep.
The benefit of this is it's a much clearer image. It's just instead of the light having to pass through multiple layers of glass, it just goes directly into the camera, basically.
Yep.
Kind of like just
reflection.
Right there, and the reflection in that is a lot less clear than the actual image that you see of us. And if this also produces a much higher magnification, which I'll eventually see. But
Final telescope, you've seen this before. Another thing we added was an aimer kind of thing, where if you align all three crosses in the same place and you look down from below it, you'll be able to aim where you're trying to go.
Yeah, the stuff in the center of the crosses is directly where you're
There's all the circuitry,
Here's the results of the prime focus method. I'm just gonna set the speed to 2x, make things more obvious.
You see the moon slowly coming in. Well, you just stick back a little bit. You can see the moon slowly coming in. Camera quality isn't the best in this video.
But anyways, and like the moon is moving like right now because of like the Earth's rotation. I just set it like ahead of its path and just move slowly in position. And you can see it's pretty high magnification. Anyways, you get the point of this.
Yep.
Here's a slightly better image. For this one, I focused the thing better, and it's rather than using the iPhone camera, this is the actual actual image produced by the camera itself.
Yeah.
Yeah, it's a lot better focus. You can actually even see like the depth of the craters. There's a shadow. There's the light from the sun. Yeah.
And it's a lot less exposure.
Yeah.
So some errors that we ran across, one of the main ones is we live in Pittsburgh, so this is kind of a given. But like cloudy skies, you can't really see anything up there when like at night. Website you could use, but like it gives pretty.
Yeah, like basically it's cloudy every other day.
Yeah.
And also right now, like the telescope just got finished. So in these right now during in these few weeks, it's a rather boring sky. There really isn't that much we can observe. There's the moon and there's Mars, and even Mars is very difficult because there's like 2 hours that we can observe it, and then it goes below the trees.
And our original goal was Jupiter and seeing the stripes on Jupiter, but we couldn't really do that because of
there's a single hour where it's actually visible, and even then it's still pretty light.
It's still pretty light outside, yeah.
And then it goes below the trees. And yeah, and like Andromeda Galaxy or Nebula, those things are
all below the southern hemisphere right now.
Wow, kinda And like here's also like the camera switch. The reason why we did this, well, as I said previously, is for a much clearer image.
These were the images of Jupiter that we did manage to get, but the first one, of course, was the camera was focusing on the lens, not of the image inside the lens itself, and
it's quite a blurry image. It's like, of course, a bunch of white noise around it. You can't really see any detail. Here's a slightly better version of it. Basically, for this image, I was able to trick the camera into focusing on the correct thing. Like, here's the lens. I would just put the camera on the side so it would focus on something farther away, and then just swiping in front of the lens, take the photo before it had a chance to readjust its focus. And like you can see from here, it's not a passive image. It's still rather blurry, and in this case, it blurs because of spherical operation instead of just a badly focused lens. Like you still can't see any detail on Jupiter itself, and because of chromatic aberration, it's a pretty bad lens. It's not a good lens. It doesn't account for a lot of things. So you can see like there's blue, there's red. Yeah, that doesn't actually exist. And like the goal was to get something like this, where you can actually see the stripes.
And you could see the stripes through the telescope if you looked at it through your own lens, but
through your eyes.
Yeah, through your eyes.
Yeah, that's why we pursued that as a goal because it was already
feasible, yeah.
And here's just the actual simulation of the errors. We found an online like ray optics simulator, which the error. Here's the ideal situation: you have 3 lines. Those 2 are very closely spaced, but in bad focus, all the lines get blurred together. In spherical operation, you just see a bunch of noise. And here's just a comparison.
Further comparison, this is the phone camera and this is the new camera.
It's a lot more zoomed in. The exposure is much better. It's a lot high resolution. This region corresponds with there. It's slightly flipped, but you can see so much more detail.
You can also see chromatic aberration.
Yeah, it's the blue ring.
And there's a blue green on the bottom. Yep.
And here's the mount system. Well, here's just a demonstration of it actually working. Basically, when I press the space button, the image goes down like that.
So the telescope.
The telescope goes down.
Yep.
And so the image goes up.
And so it's self-adjusting.
I think here's just some more tests of the. That's unfortunate.
There we go.
Alright, here's the
more tests of it actually being able to move. You can see the bottom moving from the stepper motor on the bottom and the pulley being able to be controlled by the stepper motor.
Yeah, pretty nice.
Looks nice.
Alright, and here's just the circuit that actually did this stuff. There's 2 TMC 2209s. Those are the stepper motor drivers. And like originally there's motor power supply. There's 700 kilo ohms of resistance between it, so that nothing really happens, so it doesn't short circuit or anything. And when this stepper driver is run in just a stepper mode. That's basically I just tell the direction with the direction pin, and whenever I pulse the step pin, it lets current go through for a short time between the corresponding coils, like the A coil or the B coil, and that produces a magnetic field because it's your current flowing through a coil, kind of like a solenoid, and that causes the motor to spin. And some of the error with the malware, like the belt tension is
a little bit weak. It's not the best.
like it's decent, but like I guess
It can still kind of move. Yeah.
batteries drain also incredibly quickly.
We originally used NIMH batteries, but we didn't have a.
I forgot to bring my charging sounds.
Yeah.
But now we're using
alkaline batteries, which are basically half used already.
Yeah, like after
They run out really.
After only 15 minutes, they're already like half. Like they're already at like I think 1.4 volts or something.
Yeah.
And because of this, because like these batteries are rather low duty, the torque of the motors is also low. Like in the previous image, we used we used a lead acid battery, but this and that one was able to spin pretty quickly. This right now does not spin quickly. And also, our first batch of TMC2209s did not work particularly well. When I measured the resistance between the motor power supply through the TMCs, it varied between 10 kiloohms and 210 kiloohms. And one of the TMCs also burned out while I was using it, and when it burned out, just a bunch of smoke and bad smells. It was not a pleasant experience. Once I decided to measure the resistance between it, and it turns out the resistance dropped down to 4.7 ohms, which is basically a short circuit, which isn't a good thing when you have 20 volts going through.
Yep.
Anyways, the new batch has
bought a few new trim.
Yeah, it's a slightly different shape, but it's because all of them are basically exactly the same sound, like 720 kiloohms of resistance. They're working pretty well so far, and the easy burnout of the old motors also makes sense because P equals V squared over R. If that just suggests that if the previous motors drivers had less resistance, they'd get hot a lot faster, and in general just be a lot more finicky. That's our presentation.
That's our presentation. So, a question that we were thinking about is that a question that some people might be asking is why we didn't wrap around the telescope, and our answer to that would be since we're already outside, it's already basically pitch black outside when we're actually able to capture the things that we need to capture. There would be no point in basically just wrapping around the entire thing. So you can see how there's basically no light coming in from outside.
The only light is my laptop, and that can be fixed by just turning down the brightness.
Yeah.
So if you just look at the image itself, there really isn't any noise right there at all. It's a very sharp image.
Thank you.